Okay, so I'm David Terei, and I'll be talking about Safe Haskell. This is a joint work with Simon Marlowe, Simon Penn-Jones, and David Mazieres. So the motivation is that we want to be able to write a server in Haskell that accepts Haskell source code over the network and safely executes it. Assuming we, say, for example, gave GC an extra flag, say something called xsafe. And this could be, for example, like an online version of GXCI. And we obviously just can't run any code. For example, should the client send us this and we naively executed it, then we'll have our file system being wiped out. And so how can we protect ourselves? How can we sandbox this untrusted code? And what we'd really like to be able to do is we'd like a really elegant system of using the type system. And so a simple policy, for example, would be to only execute pure functions. So here you can see API defined where we have a search predicate, and given it's a pure function, we should hopefully be able to safely execute this when given something like this in the client. And it would be great if we can extend this model by using monads to sort of contain effects. And here we wrap the IO monad and define sort of a restricted version of the IO monad, where the really nice thing here is that what we can do is we can control what functions are available to the client simply by controlling what we define as existing in this vals. And so the important thing to realize here is that we don't export the constructor, the unsafe Rio here, and so it's completely within our control over what side effect functions the client can execute. And so this is like a really nice system here in that it's very sort of simple to understand, but very comprehensive in how we can sandbox untrusted code. And as I said, yeah, we can extend this model very easily just by defining the functions. And there's a nice correspondence between a monad and a security policy mechanism here. And it allows for far more flexibility than a lot of other language-based approaches, such as in JavaScript or Java, where the security mechanism you have available is fairly sort of static in nature, and it's hard to really extend it, and you have to really have it that your policy maps very well to the existing mechanisms. And there's a lot of research within this domain that already exists. Here's just sort of a couple of them. And unfortunately, while it has shown sort of great promise, none of this is actually practically deployable today, as I'm about to demonstrate. And so it's very easy, obviously, to attack this because it relies on there being no holes at all in the Haskell type system, which is trivially not true. So, for example, one of the first things we do is we use one of the unsafe primitives, such as real world, which is how the IO monad is implemented. And basically, by using the by using the real world symbol, we can implement our own version of sort of the unsafe perform IO function, and then we can execute any IO action as a pure function and escape the sandbox. And another one would be to actually use the unsafe perform IO symbol, unsafe perform IO function itself. The reason I highlight the difference here is just that we have to be aware that there's unsafe functions, not just unsafe symbols, and that there's a transitive nature here with the imports. Another such one would be the foreign function interface. So before in the very first example, we used the system Haskell function to execute iron remove. And here we do the exact same thing, but now we actually execute it using the C API. And this is possible because we can import foreign function interface, foreign function calls out as a pure function, like outside the IO monad. A final one here would be to use data.typable. So we simply create our own instance of the typable class for the Rio monad, and then we just pretend that it's the same as the IO monad. And this now allows us to cast any IO type into a Rio type, and we can now escape the sandbox again. And so there's a whole bunch of attacks that are available like this. The ones that I've just shown have been really about violating the type system directly. As well as that, there's ones that violate module boundaries, such as generalized new type deriving and template Haskell. And the way these ones work is that, as I said, we have to be very careful that we don't allow access to the unsafe Rio constructor. And using generalized new type deriving and template Haskell despite the Rio type being an abstract data type, we can actually bypass that. So we can gain access to the unsafe Rio constructor, even though we didn't export it. It should be a private symbol. So pretty scary stuff. And then we can also change the code on the server. So the client can change the server's code using rules and overlapping instances. And so what we'd like to do is we'd like to define a safe subset of the language where these kind of attacks aren't possible. And as I said, we're going to compile code in the safe subset using the xsafe flag. And the intuition here really is that we want the problem that types never lie, so that the client code can't lie about its types at all. And so just to sort of give a demonstration here, in the case of like a foreign function interface that is masquerading as a pure function, should we compile with the xsafe flag, then we should have an error code, like a compilation error code like this, that you're only allowed to use FFI if you actually keep it inside the IO monad. And so the second step here is that all those attacks I outlined are to do with unsafe features in the language. But unsafe 4.0, for example, is simply a function that is using these and re-exporting that functionality. And so we need to contain these unsafe features in a transitive fashion in terms of the import graph. And so the other part of the sort of the safe Haskell story is how do we track all this and how do we contain this and reason about sort of when a module can't be trusted in a transitive nature. And so one way we could do this would be to only allow modules that were compiled in the safe language to import other modules in the safe language. And while this would work, it's far too restrictive for our liking. For example, we may have a client that sends us code that imports the bytestring module, and then this story, then bytestring would be considered unsafe and compilation would fail. And this is not really acceptable to us. Bytestring is generally considered a fairly safe to use package. It gives you a pure list-like interface just on top of unsafe internals. And so we want to be able to talk about when can we trust the module and the package to provide a safe interface on top of unsafe internals. And so this brings us to safe Haskell. And so I'm going to kind of try to describe safe Haskell through a diagram and sort of build it up. So to begin with, we have the Haskell world, and we have modules that use only safe features of language, and we have modules that use unsafe features of language. And I'll be using red to say that the client can't import such a module, green to say they can, and gray to say when compilation failure should occur. So to begin with, safe Haskell will actually infer the safety property of a module. So as well as the client or server being to explicitly state it, GC will actually infer whether or not the module is using the safe features of the language. And we have a concept of safe imports. And so we just give you this little bit of extra functionality that when you talk about an import, you can state whether or not it should be considered trusted. So when compiling with -xsafe, all imports have to be have to be safe imports by default and are implicitly safe. But in some of the other sort of options, we allow you to control that. So one way you can talk about the modules, you can actually assert that it's unsafe, and so obviously that will allow it to be imported and should reside down at the bottom here. Another is that you compile a module with the xsafe flag, and assuming that all the imports are trusted, then you're good to go. And if some of them aren't trusted, then a compilation failure should occur. And another mode that we support is the trustworthy mode. So this is designed for being able to handle cases like bytestring and sort of give a bit of extra functionality and flexibility to the deployment model. And the thing with trustworthy is we don't place any restrictions on a trustworthy module in terms of whether or not it can or can't use safe features of the language. And so we need a way of controlling when, if a trustworthy module should be considered trusted or not. And so what we do is while a module author will state whether or not they believe their module to be trustworthy, such as the bytestring author, it's up to the server then to say that they trust that author, the author of the bytestring package. And they do that by basically saying that they trust the package. So they'll say that, okay, well, bytestring said that it's trustworthy, and I trust the bytestring package. And in that situation, then we will consider the module to be trusted and safe to import by a client code. But if the server doesn't trust the package, then we won't consider it safe to be imported by client code. And so that kind of gives us the terminology that we're using here. So safe being this kind of area up here, then trustworthy, and then unsafe. And that also gives us the formal definition of how we're checking the outlook for trust. So there's two cases. One where the compiler itself can check that a module M is worthy of trust. So in this case, M has been declared safe, and all of M's direct imports are trusted, and compilation succeeds. The other one is for trustworthy modules. So in this case, the server administrators stated they trust the module M. And so here M declares itself trustworthy. The package that M resides in is trusted by the server administrator, and all of M's direct imports are considered trusted. So just to cover trust a little bit more. So as I said, it's kind of like a bit of a control escape hatch into what you want to allow safe code to be able to import, such as the byte string package. And so the guarantees that say Haskell offers in terms of whether or not types can write is really dependent on what you as a server administrator decide to trust or not. And so package authors, such as byte string package or others, should really be careful about considering when they don't label a module as being trustworthy. But in the end, the onus is really on the server administrator, that a malicious package author could very easily state anything as being trustworthy. And so use the server administrator, the onus in the end is on you to validate that you trust this package indeed. And this is just kind of showing the syntax of sort of the safe imports that's available when you're using the trustworthy pragma. And the point here is that it just gives you a little bit more sort of flexibility here, that you might use a package author, or some module author might decide that I want to declare my module trustworthy, but I only want to say that in the condition that one of the modules I import is considered trusted by the server. So just to walk through an example here, the question is, does the server administrator trust the module London? So is the module London safe to import by client code here? And so here we have the module London is trustworthy and lives in the England package. And so to begin with, we know that the server administrator trusts the England package. So two of the conditions so far have been met. And the final one is we have to check that the safe imports are indeed trusted. So here, IO unsafe is not imported as a safe import, so it's fine, while Paris is imported as a safe import. For Paris, it's compiled in the safe language and compiled safely and has no imports, so that itself is that itself is enough. We don't need to worry about whether or not the France package is considered trusted or not, because the machine checking here is sort of enough of a guarantee. So a demo time. The GCR line that I was talking about earlier is something we've actually implemented as part of this work. And based on the security policy you can see on the screen, it's just those couple of lines. The reason it's wrapped into IO monad is so there's a tiny bit more, we actually extended it last night so that you can use the put string function. And otherwise, you have no access to any IO performing operations. So if you, don't do this right now, because this is untested other than myself really, but if you go to gkc.io, you'll get this. And you can do hello world in the browser. Great. Now, though, if we get a type error. Let's see. Okay. So here we see that we're trying to execute inside the reader monad, and unfortunately you're trying to execute an IO performing function, so we get a type mismatch. And we have the sandbox working. Another great thing we have access to that might help explain things a little bit is we have an isSafe command now. So I can do isSafe system.io.unsafe. And here we get all the properties. So the simple one here is obviously the module itself is regarded as unsafe. And so regardless of all the rest of the stuff here, the end result is that system.io.unsafe is not trusted. A slightly more complex one would be data.map. So Data.map itself is considered a safe module, but the package it resides in is currently untrusted. And we have here the dependency list of what packages that it depends on need to be trusted for this module itself to also be considered trusted. And so we have two here. One is that the base package needs to be trusted, which it is, and the other is that the containers package, the package that it resides in, actually needs to be trusted, because somewhere in the data.maps dependency chain, it imports a trustworthy module residing in the containers package. And given that containers is not currently trusted, the end result is that data.map is not trusted. And so should we try to import it? We get an error. So, yes. Okay, and so one of the questions here is, how safe is Hackage? So how usable is this system, and how sort of deployable is it right now? And so one of the things we did was that we compiled basically all of the code on Hackage, and we figured out what modules were inferred right now as being safe and what were inferred as being unsafe. So how much of the world right now is usable out of the box. And basically we found around about 30% of modules currently are being inferred as safe, and about 70% are being inferred as unsafe, out of about 14,000 modules. A second test we did was to look at how many whole packages compile in the safe subset of the language. So as I said, the safe subset can be thought of in two parts. One is restricting access to unsafe features, while the other is restricting imports. In this test, we didn't restrict imports at all, we just restricted unsafe features. So a package importing system.io unsafe would compile fine, but one using template Haskell or pure FFI imports would compile. And basically found here that about 80% of them were fine, and they would compile with the restrictions on template Haskell and generalized interrupt deriving, and only about 20% would fail. This is a breakdown for the reasons of the failures, with about half being for generalized interrupt deriving, a third for template Haskell, and the remainder is split evenly between typable instances and foreign function interface imports. So going forward, generalized interrupt deriving should be solvable. It was open sort of, it's been a bug that's been known for a while, but how to solve it wasn't figured out until about a year ago. Typable also should be somewhat solvable in the sense that there was previously more of a need for handcrafted instances because there were some types of GC you couldn't derive. But now that we have polymorphic kindness, that should be something that can be solved. And furthermore, there are a bunch of unsafe functions in the base package that just live in normal modules like the ST module, for example. And they're being deprecated and they're going to be moved to their own unsafe module so that then they won't be sort of affecting as much code as they currently do. And one thing I kind of want to sort of, I guess, use this podium for is a bit of a call to arms. That what we would like to say to the community is that, as a language designer with say Haskell, we should really be thinking about how to make your extensions safe. And going forward, any new extensions should really be putting a bit of thought into, whether or not they can be included in the safe language, and if not, sort of how the stress can be resolved. And as a package maintainer, sort of the same story goes. While obviously, you should go out and use the functionality you need best, separating your unsafe functionality into sort of unsafe modules and then to regard your primary modules as being safe or trustworthy is really the way forward we'd like to see the community move. And so this has been implemented in GHC since 7.4, and you can find more information at this address, and you can play with GHC online at this address. Thanks.